Okay, well, welcome everyone. Just in case you were not at the launch meeting a month ago, my name is Yu Ding. I'm a professor at the Georgia Institute of Technology, Georgia Tech, and I recently relocated to Georgia Tech. I was with Texas A&M University for 20 plus years, been working on wind energy research for probably about 20 years. And but myself was trained as a data scientist. I am one of the members on the organizing committee of the IEC Wind Task 43 on digitalization. So this is the effort to use wind platform and to conduct some collaborations. And Sarah Barber very nicely offered the platform and to provide the support. And Sarah and I organized one of something called challenge on the power curve modeling last year. And this effort on the turbine performance assessment and quantification is really kind of continuation of that effort. Instead of calling that a challenge, I thought it's probably better just we call it a collaboration, because we don't really challenge anyone on anything. We want to work together, discuss this issue, and then probably to have some kind of consensus, even to come across a better method and with more robustness and applicability. So that's basically a brief recap of the purpose of this particular wind farm space and collaboration effort. So today is the second meeting, the second monthly meeting. And so I would invite you, if you have not done that yet, I would like to invite you to visit the We Do Wind space. Let me share the space with you. So this is a We Do Wind space, right? All the important information is here. And Sarah particularly stressed the importance to have all the technical discussion to be archived in the space. And so far, we haven't had a lot of this kind of discussions, but should anything, the discussion start rolling in the future, we want to use this one as a basically mechanism to archive the discussion, the results and insights, conclusion, if we have any of those things, right? So there's primarily two important posts right now in the space, right? And if you sign on the space, and once you log into the We Do Wind, I believe you will be able to find this data-driven turbine performance analysis space, right? I have a few other space, but you click on this space, you should be able to see the two important posts, right? One is the description of this collaboration, another one provide the data sets we're going to use, at least for now, okay? And today, the primary focus is I would like to go through some of the method, at least I know of, some of the method developed by my own research program. And I also like to invite all the participants interested in this topic, and also have the experience on this particular topic to share your thoughts, right? May not necessarily be today, we try to leave some time for discussion toward the end of the meeting. And but we're going to have a monthly meeting going on. So on the March meeting, Florian Hammer from Switzerland is going to OST, is going to share his research on this particular topic. So we try to line up the future speakers. If you are interested, you have something to share with the group, and please send me a note, that way we can kind of schedule you, announce to the rest of the group. And also at some point, we are starting to do some of the exercise, and by applying some of the method to the data and to see what kind of result they produce, right? And then does the result make sense? Is this result better than that? What is the caveat and so forth, right? Hopefully, we don't really necessarily because we know everyone is very busy, we only meet once a month, and but I think the accumulation actually will produce quite a bit of knowledge for the body. So if we keep going this way, and by the summertime, my feeling is that we're going to make quite a bit of progress. Okay, so without further ado, and let me get to today my presentation is what I want to do is just briefly review several existing performance comparison methods, and some of the methods you are already familiar with. And like I said, if you are familiar with the other method and different from any of the above, you are welcome to present that at a later meeting, right? Just send me a note, right? The very first method to be used for the turbine performance comparison is probably the so-called side-by-side comparison, right? The idea is very simple because you want to have one of the turbine. Suppose you have technical change at this particular time point, right? By comparing the energy, the E represent the energy before and after the technical change, it's very hard for you to separate the energy change is due to the technical change itself or due to the weather change before and after, right? And in order to control for that kind of weather effect or so-called confounding effect, people said, let's use a pair of turbines. One, we call it a control turbine on which no technical action was undertaken, right? Another is a test turbine, and on which this particular technical action has been undertaken. And then they are close enough. And not only they are very close enough in the physical velocity, and which implies the very much same, at least a comparable environmental condition, but also we would like to have these two turbines of the same make, same model, and on the same terrain. They probably enter the service at the same time, has deteriorated in a similar fashion, right? And then what you need to do is really to use the control turbine, right? This is the delta energy from the control turbine before and after, and then you do the delta test before the test turbine before and after. The difference between the test turbine and the control turbine, assume the control turbine really capture any change is due to the environmental change and other things not related to that particular technical action. And the difference of the difference can be reasonably attributed to the technical action being undertaken, right? So this is a very simple idea, has been going around at least for 15 years. One of the very first paper or poster floating around this idea was traced back to 2004. And some of the critiques of this method says, they always involves a pair of turbines, and some of the small wind farm doesn't necessarily have that kind of luxury, and it doesn't produce a turbine performance metric in and by itself, right? Suppose you only have one turbine, you want to, track the change of that particular turbine, and you cannot really exactly do that, right? And Smart Blade is a small company in Germany. They published a study a while ago to say the side-by-side comparison works. However, it doesn't work very well if you use a scattered 10 minutes data, and you have to use a very high frequency data, like 1 data point per second, right? That's one of the viewpoint and of the side-by-side comparison part. Another commonly used method is use power coefficient, right? The physical law says the wind power production is related to the air density, the swept area, which is the square of the radius multiplied pi, and the cubic law of the wind speed, and also the power coefficient, right? The power coefficient, if you know the power, air density and the wind speed, you can calculate that. But the power coefficient is not really a constant, it's actually a curve, right? Also because of the turbine controls, the power, the cubic law is not really always true, right? Once it starts bending to the saturated power or the rated power, that's not really the cubic law anymore. And also the power coefficient is a function of the tip ratio speed, which is take the wind speed as input. So that complicated the overall relationship between the power and wind speed. So even you calculate this power coefficient, like we said, it's not really one constant. It's rather a curve. And oftentimes this power coefficient curve is plotted against the tip speed ratio, right? When you have a curve, it's not sometimes very easy to use or compare. So people tend to use the so-called peak power coefficient to, as one of the single scalar to do the comparison, right? So sometimes people said we do the comparison based on power coefficient is actually precisely the so-called maximum or the peak power coefficient. It's upper limited by the Benz limit, of course. That's the physical limit for the power conversion efficiency. The IEC 61426-2 specify a production-based availability, right? And that's as a opposed to time-based availability. The production-based availability, the idea is very simple, right? You basically have the actual energy production and versus the potential energy production, so that ratio. But the potential energy production need to be calculated by adding the actual energy production and the lost production. The lost production is really caused by abnormal operation status of a turbine, and usually you need to really have a lot of intimate knowledge of that turbine operation and the local environmental condition to decide on that. In one of the simple way of doing the calculation is to use the power curve to approximate the potential energy production. So instead of have every single detail of the production process, and you can use the wind speed and go through the power curve, which you estimate from the normal or good operation period, right? And then to say this is what we expect of potential energy production, and then you can add all the actual wind energy production as measured from the turbine to give you a ratio. And of course, this is approximation. This is not exactly the production-based availability as specified in the IEC standard, but it's it's quite close and much easier to use. When we compare, in one of our previous study, when we compare the PGR power generation ratio, this index defined on the previous slide, and the CP, the power coefficient, and we find there's some interesting relationship. Number one, the PGR is roughly can be seen as double the CP, okay? And they are not exactly as a double, and there's a lot of noise in the data, so it's not every single data point is really double the CP, the peak CP. But if you plot all the data on the scatter plot, you will find the best line fit is almost the slope is 2. Okay, when we use the weekly data, if we have the data to calculate the PGR and the CP on a weekly basis, these two index has a correlation of 79%. This is use multiple year offshore wind farm data, right? Use other wind farm data, the correlation could be somewhat different. Use monthly data, when you really kind of average them more, you use less time resolution, the correlation increased to 93%. So there's a lot of commonality between these two ratios as a measure of the turbine performance. In the end, these two indices have different kind of nature, right? As we explained, the CP is really peak CP. They represent the maximum effect. The PGR is integration effect, or it's average effect. So if you look at the figure to the right, this kind of very high bars are the large difference happen for that particular period between the PGR and the CP, right? The smaller bar, the very light gray bar, is really, really small differences. This kind of intermediate bars are the medium difference. But the very large, very dark bars doesn't really happen that often, indicate the big difference between those period. There's a big difference between the PGR and the CP. When we look closer into those periods, and we find this is really happen when this CP has quite a large number, but the average is small, right? So this probably happened, in the part of that period, like a week, right? Only a day or two, you have pretty large CP, but the rest of the days, you either lost the production or you have relatively smaller the efficiency. So the average of the PGR is small, but the maximum value of the CP is large. Okay. Another productive efficiency metric actually invoked production economic study or theory, right? So I'm not sure the audience in this group how familiar you are with this economics theory about the production efficiency, right? There's this well-known theory, they call it the efficient frontier. The basic idea is this, right? Suppose we take some of the firms, right? A company, we call it D, E, and F, the three companies, right? And then people will argue the company E is more efficient than D. The reason is if you look at the D and E, they take the same input. The input could be labor, could be capital, could be material, or combination of those, right? They take the same input, but the E has more output than D, okay? And also the F is more efficient than D because they take a different input, obviously, but they have the same output. By reaching the same output, the F actually uses less input. It's hard to compare F and E because they, use a different kind of input, has a different kind of output. But nevertheless, if we use a line to connect the dots on the outer skirt, out layer of these different companies, and then the point on the very out layer represent this kind of frontier, right? Is for all the interior point, you are either using more input for achieving the same output, or you use the same input, but you have less output. So you are not going to be as efficient as those points on the efficient frontier. So that's the basic idea of the so-called production economic theory, right? How you identify the most efficient. So the same thing is like for the wind turbine. Each wind turbine is treated as a power plant, right? So suppose the D, E, and F is one of the wind turbine, and then you can compare one of them, right? And even for one of the wind turbine, if you get all this kind of data plot at the different kind of weather conditions, if you generate this the wind power curve, you will find if you have an average power curve, which is the blue part, and then by using the production economic theory model, you can calculate a kind of efficient frontier among all this kind of individual data measurement. The gap between that is what they call systematic inefficiency, right? You can achieve that part, and then if you measure how much potential you can achieve that part, or you haven't really kind of get to that gap narrowed down, is your efficiency measure, right? So the production economics model is a little bit more complicated. I think this part has not been thoroughly studied and used in wind energy research, but there's some initial effort. One of the things in order to do is define this so-called systematic inefficiency, and then to estimate this so-called efficient frontier function. But the economic theory also requires those kind of curves to follow certain kind of shape constraint. They cannot just be arbitrarily shaped. So in this particular setting, the shape constraint says at the beginning part, this is a power curve. But this power curve with the shape constraints, and the beginning part should be a convex, and the ending part should be concave, and then in the middle is connected by inflection point. Okay, so basically this becomes there's something called the shape constraint power curve estimation, and then you need to estimate the systematic inefficiency part to shift the average power curve, which we call the G, to the F curve, is the efficient frontier. And then the productive efficiency is really being defined by this ratio between this G curve and F curve. If the G curve is so close to the F curve, okay, and that means you don't really have much inefficiency remaining in your system, and then your system is pretty efficient, right? But if the curve is large, that means on average you only get the G curve, but you actually have potential to get the F curve. And then there's a big gap in between. That means your system is not really performing very efficiently, right? The study we did on this part, and we also find the production efficiency and the power coefficient has a pretty high correlation between each other. So they are not really kind of entirely unrelated to each other. By using 4 years data, and we will be able to calculate something between a 75% correlation between these two metrics. But they also give some differences, right? Here's two examples. The upper part is the productive efficiency, another lower part is the power coefficient of the 4 wind farm, 2 onshore, 2 offshore. And you can see their pattern actually is reasonably consistent and similar, right? But be aware of the power coefficient is a peak effect, and the productive efficiency, just like a PGR, is integration effect. So the integration effect is sensitive to the entire wind spectrum, and the peak effect was not, right? They're kind of sensitive to where the peak of the coefficient CP happens. And we use one of the simulated data. This is published in one of the paper in 2007. The simulation was designed by them, it's not by us. And they try to simulate, the effect of the dust accumulation on the wind turbine. So they basically said, suppose this one happened, reduce the power production coefficient by 3% per year, and we do that for 4 years. But the particular design in this 2000 paper, and by and large affected the power for the wind speed 9 meters per second above, right? When you use a power coefficient, you cannot really detect that. I believe the peak power coefficient happened around like 8 meters per second, between 7 meters per second and to 8 meters per second. And by using the productive efficiency, you could detect that. And the recover sequential reduction is 2.4%. It's not exactly 3%, but it's close. So this is another method. And just one more point about this shape constraint power curve. If you have a lot of data, it doesn't really make that huge difference. It does make some difference. It doesn't make that huge difference. So we actually fit the power curve by using the shape constraint and the IEC standard procedure, right? If on the large, the zoom out plot, you only see a small difference. And when you zoom into this particular small area, you find the difference is more pronounced. And the IEC procedure doesn't really, unless you smooth out, even you smooth out, it probably doesn't satisfy the shape constraint. So this part depends on how many data points you have, and may or may not make a really appreciable difference. Yeah, the last method I want to go over with is one of the method we actually implemented in our package, the DSWE package. And this one invoked the causal inference method. If you recall in the first meeting, I mentioned the causal inference has 2 aims, right? One is determine which factor has a genuine cause and effect relationship with the response, which is the power production. Another one is quantify the effect on the response and due to certain kind of action taken, right? It's different from when we have controlled randomized experiment and versus we have a natural experiment and we don't really have full control of all the conditions. We only have the data randomly observed. And this is where the causal inference method help with and achieve mimic at least some degree of control, and then to be able to separate the confounding effect versus the testing effect, right? The true effect. And this particular procedure includes 3 components. The first component is basically a non-parametric power curve, right, to determine the genuine cause and effect relationship. The second one is try to create a probabilistic comparison setting for the comparison, right? This is really try to mimic, even use a natural experiment, but try to mimic the condition which you could possibly to do the controlled experiment, what's going to be, what is going to look like, right? The last part is quantify the effect due to the action, and also is uncertainty. And we do have the package implemented in R and also Python, and it's called DSWE, right? The Python is on the CRAN, so if you have on the CRAN, you can load the package and run that immediately. So this is the package I think is well documented, and also goes through the CRAN's initial screening process. They make sure it runs before they can make it available on CRAN. Okay. The first one is a non-parametric power curve. So I'm not going to spend too much effort on this one. This is exactly the reason we conducted the power curve modeling challenge in the first part of 2023. Right. There's a lot of options you can choose from, right? We would recommend using our own, we call it TempGP power curve model, but you are welcome to use other options, right? The TempGP power curve model used to be slow. We recently added acceleration element to the TempGP. So if you use a full year data to feed a power curve, it probably just takes you a couple of minutes, right? The second part is the so-called correlated matching. This is really kind of trying to mimic the randomized control effort from natural experiment. We invoke one of the very basic idea from Don Rubin, the statistics. Statistician really developed this kind of idea previously. So without diving into the mathematical details, I just want to use the figure to give you a sense of what to be accomplished here, right? So before the comparison, right, you have different kind of wind speed profile, you have different kind of temperature, you have some other things. By using this procedure, we basically down select the data condition to have more comparable, not exactly the same. We only can achieve the probabilistic comparable condition, right? So we want to make sure the probability density of those kind of conditions before and after the action is more comparable. You know, this is really after the causal inference action, is before and after, and this is temperature before and after, right? And then once you do this type of alignment, data alignment, and the data selection, you will find the delta energy here is more credibly attributed to the turbine inner change, which is because of the technical action you have undertaken, right? The very last part is also a comparison, right? Once you be able to do that, you still want to quantify how much a difference in terms of the percentage of AEP improvement, and also what's the uncertainty, right? We did this kind of analysis to compare 2 non-parametric power curve, and also attach this 95% confidence interval to that, right? So this is a 2 comparison. Suppose these 2 power curve are not equal to each other. And not only this comparison tell you they are not equal to each other, but also identify the specific wind spec region and which part of the region the difference occurred, right? In this particular example, it occurred roughly about 8 meters per second, all the way to roughly about 16 meters per second. And these 2 wind engineer, as we understand, is quite important because sometimes they make a change, they have the anticipated where the impact, the effect is going to be. And this helps them to come double check. Either the method, is there something wrong with the method, or there's something wrong with their initial understanding, right? So this can be quite handy for identify those kind of information rather than simply tell you your method worked or your method doesn't work. And then if the two power curve, they still remain pretty much the same, and they are not exactly the same, right? We say they are pretty much the same, is they are within the 95% confidence interval, and the noise is to this level, your difference is not really go above the noise, okay? And therefore, and we cannot declare the two power curve is different. And as a quick recap, and I went through some of the turbine performance comparison and quantification method as I know about that. And there's a side-by-side comparison. This is one of the very distinct method and has been around for a long time. The power coefficient method, and the other three methods we reviewed here, they all kind of based on power curve one way or another, right? The simple one, the power generation ratio, the PGR. A more complicated one is the productive efficiency, which use the shape constraint power curve and also invoke the production economic theory. And then the last one is the causal inference and the curve comparison, right? This one we implemented in the R package. One of the nice things is it gives you uncertainty quantification, not only on the effect, but also give you specific wind spectral region and where the difference actually occur. Okay, and today's really the recap based on the three papers and also the book I published, the chapter 7 of that particular book, the data science for wind energy. And the book right now is open access, so you can download the book free, and all the data and the code and also has been released since the publisher of the book. But recently the publisher agreed to make the book free access, open access. I think I'm going to stop here and probably take some questions and do some discussion. I hope I didn't really go through this whole thing too fast, but if you have any questions, we have about 20 minutes, and I'd be happy to have a discussion. So Yuri, I see you raise your hand. Any comments, discussion, thoughts to share?
Maybe just one thing to add in terms of that side-by-side comparison. There's a kind of alternative to that that's become quite popular among turbine manufacturers for software upgrades, where I think some of them call it a kind of swap test. And the idea is basically that you have some new optimized control algorithm either at the turbine level or wind farm level, and then you run your old software 10 minutes and then new software 10 minutes, and then you keep doing this for a few months, or the interval can be different. It could be 1 hour off, 1 hour on, but you kind of try to find like statistically similar distribution for the before and after implementation. And I suppose if you do this kind of shorter periods, then you might have higher chances to have more similar distributions. But of course, it only works with the software. You can't do this with hardware.
Right. I heard about that too. Yeah. So, like you said, certain things, for example, LEP protection, right? If you want to compare different options, and that cannot be done. You cannot just apply, take it out of this kind of things, right? Yeah. For the software, some of the software things can be done. I actually talked to one of the major operator. They is in China, so they are also OEM for the turbine, and sometimes they reluctant. Even it's doable, they kind of reluctant to do that, and for different reasons. And Some of the software upgrade, it takes longer time, right? They kind of to use that once they upgrade it or they switch to the new system. It's not easy to kind of switch it back anymore. So this is kind of limited to some of the things, like you said. It is really easy to switch back and forth in those 10 minutes half hour period. Yeah, I can make another slide to add to the PowerPoint to basically mention there's an alternative for this kind of quick switch back and forth. Yeah, that's a good point.
But I suppose the main interest for this group is to find a statistical method for doing it on an individual turbine basis.
I believe those kind of method, the switch and back forth, serve its purpose, right? It just doesn't really, solve all the other things. So we would like to have a method which can have a broader applicability, right?
Yeah. Because either for physical reasons you can't do the swap on and off, and of course, even if it would be possible, you need to have all parties agree that that's going to happen, and there's always going to be a lot of cases where it doesn't happen. So it's a kind of a niche thing, I suppose.
Right. Clement?
Yeah, this is Clement speaking. I just had a question on the method I think you presented where you're trying to capture, I'm not sure I have the name right, but just like this systematic and certain inefficiency between the inputs. That sounds kind of a very interesting way, but how do you deal with if the anemometer of the turbine is wrong? Like, because you could also have like the two turbines are seeing the same wind, they produce the same power, but for some reason, one anemometer is biased. And so then in that case, you can see the power curve being shifted. And I guess with that method, you're kind of blind to that. So have you ever thought of a way to come around this or not?
Yeah, I think that's a really valuable point. All this method, I think probably to some extent the side-by-side probably is more immune from that issue because they don't really directly use the wind speed per se, right? They use the wind power directly, but almost all the other method has some of the issues related to, how you're going to treat this for example, the transfer function change after you did something to that blade, right, to the turbine. That's actually one of the topic Florian Hammer is going to discuss on March meeting. So he did some work and kind of focus on that particular part. So in the current method, that's kind of remains the open issue. The production, this inefficient, the systematic inefficient part is going to be affected by the anemometer change or bias, right? So the method itself, in and by itself, doesn't really kind of address that. To answer your question in a short manner, yeah. But the other method is subjected to the same problem as well. So I think that probably will be one of the quite important but a separate issue to be dealt with together with the rest of the algorithm.
Okay, thank you. Yeah, and have you tried, I don't know, using like channels that should be related to wind speed that may be less prone to bias? I don't know, like the generator speed or something. So using generator speed versus power instead of using anemometer wind speed versus power.
The generator speed sometimes tied too closely to the inside of the turbine mechanism, right? They're driven by the wind speed anyway. So from our previous studies, we don't really see that big a difference between you use the generator speed and versus the turbine speed. That bias is probably still going to be there.
Okay.
So there's a couple of other things people tried. I didn't really entirely include in this presentation. The two things come to my mind is one is there's a new anemometer being designed and also being marketed, right? At least one of the German company does that, which is use the anemometer. It's really measure the wind speed in front of the turbine rather than on the back of in the wake. Okay. My understanding is that new anemometer is still not very widely used because it's much more expensive than the existing anemometer. The second one is we did a study with the EDP Renewable a couple of years back, and for them, one of the way they improvise try to avoid using this kind of anemometer in the wake, but affected by the test turbine when the transfer function has altered, is to use another neutral turbine. So instead of use a pair of turbines, they use 3 turbines, right? The one is a neutral turbine, basically just provide this kind of wind measurement. It's in the wake, but it's in the wake of the same type of turbine has not been altered. And now you have it's close enough to the control turbine and the test turbine. So that provide a kind of unchanged reference to the wind measurement. The problem with that approach is you need to have 3 turbines close enough, which assume satisfy all the assumptions we previously mentioned, right? And in some of the large wind farm that happens, in some of the small wind farm it doesn't. So there's always a pro and cons of all this kind of treatment.
Another possible solution to that is NREL has a paper out on consensus-based optimization, where you would use, a collection of neighboring turbines to estimate a consensus wind speed, and then you could just use that. So does that be similar to the EDP one, where you use this neutral reference for the turbines? Would be something you could consider.
Okay, so are you familiar, Jonathan? Are you familiar with that kind of work? Is that something you want to, or you're available to present? That way we can have a discussion on that.
Yeah, I could see. Yeah, I could probably do something on their approach and how it looks compared to other things. Basically review the NREL concept. Right. Yeah.
So are you available to do that probably with the Florian, because Florian is going to discuss that very issue on March meeting, okay. March 11th. So if you can do that, probably provide the 2 different kind of perspective, because I understand this is very important. You need to make sure the input is accurate enough before you can see what kind of assessment it's going to produce, right?
Sure. Yeah, I could work with Florian. We could get in touch, and maybe it's just he does his part, I do my part, but we can see.
Yeah. I think that sounds fine. Yeah.
I didn't expect to get homework today, but that's cool. That's fine.
No, we want to engage our participant. That way, we probably can keep you a little bit longer, right? Otherwise, if it's my monologue, everyone can really bored. And next time, I'm not going to see you anymore.
No, absolutely.
Hey, Aris.
Hi there. A question from my side about in regards to this wind speed problem. Has anybody ever considered using reanalysis data for that work? Satellite-based wind speed measurements to build wind speed measurements on site based on reanalysis data by downscaling it with correlation or with model, and then using that, which then it's consistent, and that it will be consistent. I think you solve the problem of consistency. It might be that you create other problems. Just a question if anybody has actually thought about that and done some work on that.
Not to my knowledge. I can sense the reason is probably the satellite data for the wind measurement is not accurate enough down to the earth, to the very near ground. Because you really want to, when we do the turbine power curve analysis, and even for the wind speed measured on the nearby turbine, if you use that one as an input to generate a power curve for this particular turbine, you're probably going to be off quite a lot. if you have some of the wind speed measured on the upper part of the atmosphere, kind of downscale to the near ground places, which is only about 100 meters above the ground, that kind of extrapolation and bring quite a bit of uncertainty and also inaccuracy. So I would say that probably is one of the major reasons. If you look at the operational wind power curve being used, they all recommend use the in situ measurement, right? Even the IEC standard.
Yeah, that's true. However, and I don't. It's not. I don't have a certain answer to that. It's just I've seen a lot of progress in reanalysis data, downscaling, and I mean we've done some work on looking into the correlation of the measured wind speed on our turbines and how that compares to reanalysis data, and the correlation is very good. If you have good quality data, there are companies out there that do that work. But yeah, I see your point anyways.
Okay.
I can say that we have tried with error and mirror data, and even with machine learning failed to get the accuracy of local anemometer wind speeds using the reanalysis data. There's just too much uncertainty, I think, in terms of terrain and other factors, particularly onshore. And like maybe for the consistency issue, but we've found that it's much more valuable to use neighboring wind turbines in order to calibrate the cell anemometer wind speed as opposed to reanalysis data.
Okay. Oh, that's good to know. Thank you very much.
So Philip, you mentioned for the onshore wind farm, do you see differently on the offshore wind farm?
I would more just say that I haven't really tried with offshore as much. But yeah, with onshore, I've even for particularly flat sites, still found the uncertainty to be bigger from reanalysis data than it is from just the anemometer itself or using neighboring turbines information somehow.
Okay. Well, that's good to know. The reason, I was just curious, but the particular reason caused the inaccuracy and uncertainty is not that big between onshore and offshore, right? It's really because of the kind of downscaling process.
Yeah.
So that part is probably yeah. Go ahead.
I would also say I haven't tried with something like vortex data, for example, which is supposed to be a lot more accurate than sort of error and mirror data, at least when you're looking at a particular, site.
Yeah, this is what I was referring actually to, but I understand there is a proprietary problem there, so it's not open to public access and things like that. So that's obviously an issue here.
Yeah, but that's a good discussion. Okay. Yeah, Christine.
Yeah, first I can just agree. Would be great if the kind of reanalysis mesoscale model data could get so good, but I've had come across a few cases where we had to use model data because like there was one case where a wind farm had a grid outage and we had to somehow predict what the production would have been for some insurance claim or something like that, and even trying lots of different providers of mesoscale model data, the scatter in the operational power curve, so the wind farm power curve was absolutely huge, and that was like a simple terrain, simple meteorology type site. The one thing that I was going to add about the cell anemometers is that you can, if you have many turbines at the site, you can do kind of analysis to look at consistency changes, and you might not be able to pick up like small changes and subtle things, but if any turbine is like starting to change significantly, I think that there are techniques to pick that up.
Okay. Chiro.
Yeah, so I wanted to raise one thing. I've seen some manufacturers that they have a SCADA signal called estimated wind speed. So I think they try to estimate what is the real wind speed of the machine based on rotor speed and other signals. I wanted to ask if you guys know about that and if you have any thoughts about it. I've also seen that before.
I do not know that by myself. So I wouldn't be surprised someone has tried that. So if anyone here more familiar with this kind of approach, I think that would be a great topic to present here, as related to the accuracy of the input, right? Are you familiar with those kind of things? At least come across or willing to maybe spend a little bit time afterwards and then make a presentation later. I see a two. Yeah, go ahead.
Oh yeah, I was just going to say that I only saw that once in GE turbines.
Okay.
So I know that they do that, but I didn't dig much further into it. So I'll not be the best person to.
Okay.
To
So I see
that,
two hands raised. Aris and Clement. Probably Aris, you go first.
Yeah, I only have experience. I don't think I have enough experience to present. I have experience with Vestas turbines. I know they do an estimated wind speed calculation, and this is based on rotor speed and other parameters. But my understanding is that this feeds back into the controller, so decisions are being made for let's say for the pitch angle based on the estimated wind speed, which complicates the matter even more. So I don't think it's a good metric to use actually as an indication for true wind speed value. I think it's more of a very sophisticated algorithm that they've built behind the scenes. I don't have enough information, but I don't think it's a good metric to use in particular for the Vestas turbines.
Yeah, makes sense. So Clement?
Yeah, no, just to fully agree with what Aris just mentioned. So I worked at GE, so I'm quite familiar with the channel. I don't exactly know how it works, and I will not be able to explain, but it's not probably fit for the purpose we're looking at, because it's kind of it's estimating
more
the wind
for real-time
speed.
control, right?
Yeah, it's estimating the wind speed based on the power curve. So like all the points will end up falling on the power curve. And so if your turbine is underperforming, it's just gonna give you like a lower wind speed. So it's kind of blind to underperformance in that case, because like all the points, so let's say you have 8 meters per second, but your turbine is underperforming for some reason. There is like fouling on the blades or something like that.
Right.
Instead of seeing underperformance, you're just gonna see reduced wind speed at 7.5 or something like that. So it's not, I think for the purpose of what we're doing here, it cannot really be used.
Okay, well, that's good to know. It's, yeah, that makes sense to me too. Right. So sometimes you have a lot of estimate, they become a catch-22, right? Which one goes first, and then you kind of re-estimate, and eventually the error kind of accumulate. But I think that's exactly the line of discussion is exactly we're trying to find what would be the best practice, right? We have 3 minutes left. So any last thought and any comments? Just to advertise for our next meeting in March, and so Florian and Jonathan going to present the method either they are familiar with, they come across, they worked on for how to correct the wind speed bias, and which is a very important issue in this kind of setting. And I will send out a reminder the week before so that we know. And please help spread the word to your colleagues and other people you know they might be interested in this kind of topic. And we certainly want to have a broader discussion and engagement with those who share the common interest. So with that, and thank you very much for attending, and we'll see you in a month.
Thank you.
Thank you.
Thank you.